Okay guys, welcome to this fourth video for the thermodynamics class. This will be page 9. And in addition to all the examples you have in the textbook, I try to go and find more real-life cases, okay? And I like to go into history and find significant problems that were resolved. So this one here is the one that is generally known as the Magdeburg Hemispheres problem, and this was done in the 17th century on 1654. Okay, so basically Magdeburg was a scientist, and what he did, I have a figure over here. Basically what he was trying to do is to show that the vacuum is a force by itself. So basically he had these two half hemispheres. He will put them together, and using this pump he will remove the air inside the hemisphere, so creating the vacuum inside. So the next thing was to see how much force can the vacuum create. So they attach horses on each side of the hemispheres, and they show that into public places. It was like an attraction. Okay, so if you go online, some people claim there were like 20 horses, even sometimes they say 100 horses, but let's try really to find out how many horses were needed in order to separate the two half hemispheres once the vacuum was created inside. Okay, so basically over here what we know is that we had two half of the hemispheres, okay, and the diameter is about 50 centimeters, which is not equal, but it's about 20 inches, just to give you an idea. Okay, so the problem we're trying to solve, let's say we have here the two semi-hemispheres attached to each other after you create the vacuum inside, meaning that the pressure inside is going to be 0 and the pressure outside, so all around the hemisphere, will be the atmospheric pressure. And now we have a force pulling to the right and a force pulling to the left. So if we apply Newton's equation of equilibrium, we can say what? Okay, I like to look at this equation as in the forces, the external forces needs to be equal to the amount of internal forces. So what are the external forces? We'll have 2F, and what do we have internally? We have the difference in pressure between the atmospheric pressure minus the inside pressure times this cross-sectional area of the hemisphere. So basically we know that pressure is force over area, where this area over here will be what? Should be the cross-sectional area. Alright, so if we do some basic algebra over here, we find out that the force will be equal to what? And remember that the inside pressure is 0, so it will be equal to the atmospheric pressure times A divided by 2. Okay, so now we need to know how much is, so the outside pressure will be equal to 1 atmosphere. 1 atmosphere is 29.92 inches of mercury, but I like to use the national units, 101.325 kilopascals. Okay, and we need to find in this problem, what I needed to find is the value of the force. So we know P would be equal to 101.325 kilopascals. Now the area here we know would be equal to what? Pi r squared if we use the radius, or pi diameter squared divided by 4. Okay, so if we substitute, we find that the value of the force will be equal to what? 101.325 times 100 because of the kilopascals times the area, that will be pi over 4. 50 centimeters will be 0.5 square, and all this is divided by 2. So if you do the calculation, I have it over here. This is equal to 9947.5 newtons, or 2236.3 pound force. Okay, so we found out actually what is the force that you need to apply over here in order, so on each side, in order to separate the two hemispheres once the vacuum is created inside. So now, in order to know the amount of forces, we need to find out what is the force created by one horse, or at least to estimate. All right, so let's see. By definition, 1 horsepower is defined, so 1 horsepower is defined as the power One horsepower is defined as the power required to raise 75 kilograms, which is about 165 pounds, 1 meter, which is 3 feet, in 1 second. Okay, so let's do a little review of dynamics, but again, if you don't remember that, it's fine. We know the work is force times distance, and we know that the power is basically the work done per time. So this will mean that the power is force times distance divided by time. Sometimes they replace this by velocity. So using this definition here, we can say what? That 1 horsepower will be equal to what? We need the force to raise 75 kilograms. So the amount of the gravitational force will be mg, okay, times the distance will be 1 meter, and the amount of time will be 1 second. So basically we can say that 1 horsepower will be equal to what? 75 times 9.81 times 1 over 1, which gives that 1 horsepower is 735.75, and supposedly what should be the units? Newtons meters per second. Okay, okay, but over here, remember, what do we know? Is 1 horsepower is the amount of force required, the amount of power required to raise 75 kilograms, 1 meter in 1 second. So if we know that basically this will be 1 meter and this is 1 second, we could say basically that 1 horsepower for this application produce, so 1 horse will produce a force of 735.75 newtons. Okay, so we know the horsepower, maybe remove this equal sign. The force created by 1 horsepower will be about 735.75. Okay, so it will be for 1 horse, and we know that the total force, so recalling that the force required to separate the two semi-hemispheres is 9,947.5 newtons. We can say that number of forces should be equal to what? 9947.5 divided by 735.75, which gives about 13.5 horses. So that means what? 14 horses. But what is that? Is that 14 horses on each side, or is it 7 and 7? Okay? So remember here we said that we have 2F. So this is really, we need 14 horses on each side. Okay? And like I mentioned before, I like to pick very important examples, and this one was kind of revolutionary at that time, because it was believed that in order to have a force, a medium, a substance was required. And this experiment, if you want, or this problem, was able to indicate that in this case, the vacuum, we took out of the semi-hemisphere all the substance, all the material inside, the air, and that created a force, and that force was actually huge. Okay, so basically they needed 28 horses in order to separate the two half hemispheres. Okay, so I hope you find this problem interesting, and see you next time.